Welcome everyone to this presentation by the awesome Pierre. He's going to tell us everything about developing reliable databases through simulation. So you will see it's a really interesting topic. And the fact is we are recording this video because he gave this talk 2 weeks ago for the open source data infrastructure meetup in Paris. We were not able to record it. So I kindly asked Pierre if he was okay to record it again. And this time in English, so everyone can understand it, not only the French people. And yeah, there we are. So you know what, Pierre, let me introduce yourself. And after that, I will get off the stage and the stage will be yours.
Thanks, Seb. So my name is Pierre, and I will be speaking about distributed systems and mostly how we are developing serverless databases in my company. I think this is like a good introduction of me.
Yeah, that's a good intro. Okay, so I will go away now, and yeah, the stage is yours. See you later.
Thank you. Bye. I will go quickly on this one. So my name is Pierre. I'm an engineer working in Clever Cloud. I'm used to use, operate, and contribute to quite a number of distributed systems. So things like HBase, Kafka, Zookeeper, Hadoop, Pulsar, FoundationDB, etcd also. So many distributed systems. And I'm also involved into local developer communities. So things like Java user group and other stuff. I'm also working on open source. I'm a co-maintainer of the Rust binding for a distributed database that we'll be speaking about today. And I'm living in France. I'm literally in front of the US, as you can see in the map. Quick words about my company. So Clever Cloud is a European cloud provider. We are in the platform as a service market, which means that developer can just git push their code and we are taking care of the rest. So we are retrieving the app, building it, testing it, optimizing the code. Then we are doing some blue-green deployments in production. And so this is like the easy part of the work. And then we are keeping the code online. So if it crashes, we restart it. If it needs more resources, we are adding more CPUs, for example. If you need more instances of your code, we are doing it on live, so upscale and downscales. We are doing security patch. For example, if there is like an OpenSSL CVE and something, we are capable of like deploying a patch in an hour. So this is our main product, and then we have a lot of managed services. So things like manage PostgreSQL, manage MongoDB, manage GitLab, and so on. So if you're interested, feel free to check out our websites. And I have another person to introduce. This is Bob. And Bob is this software engineer. And, you know, he's the lucky one. He's the lucky one because he obtained like this cool project. We as developer, we all know the cool project where you can just like write some code, create some stuff. There is like no deadline, and you can enjoy the fact that writing software is really nice. And Bob is like writing his software, and he's doing. And he's deploying some version of his code on Friday, because we all do that. and he's coming back on Monday, and on Monday he's seeing the face of the on-call duty people, and he's like, Bob, you know what, the weekend was awful and everything has fallen apart during the weekend. And Bob is like, oh no, did I mess something wrong? And he's like, yeah, your software just went completely wrong. And this is like tough, because like Bob is really want to improve stuff. And Bob is thinking how he could write software with less bugs. And this is tricky. And I think like every software engineer wants to write software with less bug. And this is pretty impossible, but to remove all bugs. But our duty as a software engineer is to try to have the less bug possible. And Bob is thinking how he can improve the software that he writes. And most of the people that are trying to reduce bugs are saying, I need more tests, because I can write unit tests, integration tests, and so on, and try to improve the software. It's true, but there is like problems with that attitude, because testing is really, really hard, and there is a number of ways that are really troublesome. So we have Bob, and Bob wants to write more tests. So within his sprint or whatever his commitment is going to say, okay, I will develop a certain number of features during this time lapse. So let's say I'm going to add 2 features to my API, for example. So Bob has 2 features that he wants to add. And he say, okay, I'm going to test a few things. So let's say that there is going to be 3 or 4 major integration tests per feature. There will be like more unit tests, but like the main test, the integration test, will be like 3 or 4 tests. So I have 2 features, 3 or 4 tests. Bob is kind of happy, because he say, okay, I don't have many tests to write. And Bob is like thinking a lot about, are the tests covering everything? And he's like, not quite, because as we all know as software engineer, sometimes bugs are triggered when you are overlapping features. So instead of writing one test, you need to shuffle the features. So now Bobby say, okay, so I cannot just test one feature. I need to test multiple features. So now I'm going to write for all my features, I will need to write tests with pair of features, which is triggering like kind of complexity, because you need to you will need soon to have your matrix of tests, because you say, okay, I have feature A and feature B, I need to test, and feature C, and I need to test all the combination of pairs of features. And Bob is kind of he's trying to see if he's covering everything, and he's not, because some nasty bugs are appearing when you have triples of features interacting together, and like the whole thing is getting like really complicated. And this is why sometimes you have like these big and huge code bases where the feature itself is a few hundreds of lines of code, which is really easy. But the implication and the impact on other features is really difficult to apprehend. So you're spending weeks to write some tests just to be sure that you are not breaking everything up. So the main problem here is that when you have like this huge and complex software, it's really hard to scale tests because of the feature cardinality, where you need to have this mental breakdown of all the tests that you are running, and moreover, when you are adding more features, you are just like multiplying the complexity of the metrics that you are trying to build. So this is one problem. Another problem, so this is like a bug report of something open source I was writing. The text is not really important, but I was working on a Rust application that was deployed on many servers. And it was kind of difficult to reproduce, but there was like a race condition between threads that was appearing on when the machine was pretty loaded. So the bug was only appearing sometimes, and the sometimes was really tricky to debug, and it took us a long time to be able to find the problem. And the reality is that production is injecting a lot of randomness into our beautiful and pure code. I don't know if you are doing some on-call duty. I do. And it has changed the way I write code, because now everything that I'm trying to do, like network connection, disconnection, everything, I'm just seeing how I should treat the error and how this could fail. And this has impacted how I write my code. Because like production is like a war field, and there is like a lot of things that can happen wrong. You can have latency, you can have failures, you can have errors. And this is really hard to modelize and view when you are just writing your code, because sometimes you cannot see what's happening. If you have two threads working kind of together, how can you mentally view which threads is going to run at which time? Because it's depending on the runtime of the load of the machine and so on. So this is like really difficult. And when you have a bug in it, sometimes it's really hard to reproduce, because it really depends on the awful timing that you need to be able to test. So in my example, in this particular code, it was really difficult to write a unit test that will ensure that somehow in the future, someone will not remove the code, the security, the lock that was put in place. There was like no test that could like say if thread B is running before thread A and mess up the work. There was like no test for this. But it's really difficult. And another thing that are like induced by the fact that randomness is part of the production is that we don't test enough error handling. So this is a paper from the University of Toronto that I really like. They analyzed many bug reports from specified projects. So this is like Cassandra, HBase, HDFS, Hadoop MapReduce, and Redis. And they did some analytics on the bug that are triggered incorrect data or catastrophic failures. And I really like the conclusion of the paper is that almost all of the catastrophic system failures are the result of incorrect handling of non-fatal error in software. And the 92% are really impressive. And furthermore, in 58% of these failures, the underlying fault could easily have been detected through simple testing, which means that we as developers are not taking good care about the error flow in our test. So we have two problems with testing at large scale and with difficult software. So the first problem is that we have feature cardinality and we cannot test everything. And the second problem is how do we inject some randomness into our test to match what we will have in production. So this is our two problems. So we are software engineers, and by design, we are kind of lazy. So if we have something that is, which is taking too much time to write, we'll just generate. So the main idea is that we could generate tests. And the second one is that we don't want some flappy tests. So we need to inject failures in a deterministic way to be sure that we are testing the right thing and it can be reproducible. And this is something that is called deterministic simulation. So the main goal of this is to control randomness. And it has two main principles. The first one is that everything that is non-deterministic has to be simulated. So if you're, this is really, really tricky because there's like a huge number of things that are non-deterministic. Just asking the time on the machine and your program is non-deterministic. Random numbers, time, CPU spend on task. If you have like async systems with executor and so on, having the control on which tasks are run at which timing is really difficult. Latency is another example. How can you be sure that the 10th read on disk will take like 60 milliseconds? How can you ensure that each time you will be rerun this simulation, it will have the same impact and it will take the same time? So this is really tricky. And error and failures and so on. So the main goal is to remove non-deterministic out of the equation and making it deterministic. Because if you have something that is deterministic, it can be reproduced, which means that you will be able to debug stuff on your laptop instead of production. And this is really important. And so given that, I would like to start a new trend, which is simulation-driven development, which is something that we do. And the main idea is this. So you will generate something called a seed. And with the seed, you could initiate some random generator. And then, based on that, each time you are trying to doing something non-deterministic, you can ask the random generator. Like, for example, how long this I should take to read this file. Ask the random seeded number. It will give you an answer. And this thing can be done by, well, you can just create a scenario. A scenario is like, okay, I'm going to try feature A and B, and then run, and there will be like stuff happening. And then I will be able to check the results, which means that if something gone wrong, you will see it. So for example, if you have like an API, you can create a scenario of usage. Like you are going to create a user, then depending on the seed, you will try to block the user or maybe change the email. Then you are going to run the simulation. There will be like errors and stuff that will be thrown, and then you'll be able to check. And the check is like it should have happened like this, and you will be able to check. And then you can just rerun another scenario. So this is really interesting because you can generate scenario based on the seed. For example, in one seed, you will be able to test feature A and B. And then if you are generating another seed, you will test automatically B and C. And then like this, you have the cardinality of features will be covered. So is it something used? Simulation is often used in software in the industry. In the infrastructure, not so much. So you have like, it is used in consensus algorithm. Now, a good example would be Craft, the Raft implementation made by Apache Kafka, which are using deterministic simulation to shuffle and test the network and test message passaging and check that their Raft implementation is correct. So this is like a good example. And it's also used by a few databases, TigerBeetle, which is kind of new and written in Zig, and there is FoundationDB. And FoundationDB is like really, really interesting because they are the pioneer of this technology. To give you some insights, there is a framework called Jepsen and a group of people that are trying to break your databases. And this is designed to be sure that the guarantee that the database vendor or the database developer are saying are true. And the work of Jepsen has been done to be sure that the database are robust and they are behaving like they said. And when you are seeing a new distributed systems, oftenly there is a people that are asking Afir, which is the lead developer of Jepsen, hey, is it Jepsen proofed? And it was in 2013, so it was a long time ago, but Afir said that the foundation have not been tested because their testing strategy is way more rigorous than Jepsen. And so this is like the moment where normally this talk, we have done a talk in French, unfortunately, about FoundationDB. I should try to record it in English, but you don't have to have much knowledge about FoundationDB for now. Just think of it as a distributed key value store. which is like really rock solid, because before developing FoundationDB, the developers developed a deterministic simulation framework. Sounds familiar, right? And this is what we do. They develop this thing before developing the databases. And their motivation was like, debugging distributed systems in production is like hellish. So their goal was to find and diagnose issues in simulation, so in developer mode, before going to the real world. And so the simulation framework is injecting failures in many aspects of the databases. So in I/O, time, cluster topology, those knob, those parameters that you can tune. This is something that is also simulated in some way. And all of this is happening into a deterministic way, which means that we can reproduce. If the simulation is finding something that is wrong, you can just debug it in developer, in dev mode, in your laptop, which is really nice. FoundationDB is so rock solid that Apple is using a lot this technology. They're using it for many aspects, but one of the main product that is using FoundationDB is iCloud. So if you're thinking about how Apple is storing data into their cloud, it's like a really interesting problem, because you have a huge number of users, and you also have a huge of little databases. And the question is, how can you just scale and store that much of data with that matrix of user and applications? And the answer is they virtualized the databases, which means that user one has a virtualized databases for backup, which is mutualized into an infrastructure, and they're using FoundationDB to store this. And when I'm saying virtualized, I mean it's really this. You have this small, it's called a record store, and they have like database issues, like how do you create a new index? How do you maintain them? How do you have a query planner that has that needs to use some metadata to know how to retrieve the record? So it's like really the real database problems. And we took this design and currently we are working on developing some database serverless products in top of FoundationDB. So we took this design that you can see on the right here, and we are recreating the same thing on our side. And this is not something that we are taking lightly. So CleverCloud is a 50-ish. There's 50-ish people in CleverCloud, so we are kind of small company, and we are kind of working on database stuff, and this is really hard. And one thing that was really important for us is how can we check the correctness of our work? And as it's like writing distributed storage system is hellish. And how can you ensure that? How can we be sure that for example, the concurrent online index recreation is good, is that we are not corrupting data from our users. And it was really difficult, and we searched and we spent a lot of time trying to find how we can do this. And as we are using FoundationDB, which has this great simulation framework, we thought, and this was like the true enabler of this our work and our R&D team, is that what if we could reuse FoundationDB simulation framework for our code? Because this is what we want, right? So FoundationDB is like taking care and is rock solid and so on. But how do we ensure that the code that we are writing on top of FoundationDB is correct? And so we thought, hey, let's take our code and put it into the FoundationDB simulation. So we can do that because we are doing this in Rust. So if we are taking this this schema of FoundationDB simulation, what we are capable of is that we can just implement what we call workloads in FoundationDB world, and these workloads are interaction with the database. So, for example, we have workloads that are testing indexing stuff, and we have other workloads to test metadata integrity, for example. And all of that are completely embedding into FoundationDB simulation. So the workload that I was speaking about is pretty simple to implement. So you have a tray, which is like an interface in Java, and it gives you a simulated database which behave completely like a real one. So you are manipulating the same objects that are creating transactions and so on. And this workload can be used like any other workload. So this is like a short version of a test file from FoundationDB. So I will briefly go through this. I remove some information, but it gives you the general insights. So the first element, so you have a title, and then you have these workloads. And these workloads are really interesting. So the first one is what we are trying to achieve. So here, this is a cycle test. And the cycle test is really nice. It's a simple one. We are going to create a ring of objects. So object 0 is going to point to 1, 1 to 2, 2 to 3, and 3 to 0. And the cycle is going to shuffle the order, which means that the ring will always be preserved, but the order of the link will be altered. And we are going to try to do 1,000 of transactions per second. So this is what we are trying to achieve. And this is a good test to see the integrity of the data that we are manipulating. So this is what we are trying to achieve. Now let's see what failures we are going to inject. And the first one is that we are going to introduce some random but deterministic network partitions, which is called random clogging. And then we are going to reboot machines. And so in these parameters, we are going to reboot up to 10 machines and keep at least 3 running. to give you some insights about how the simulation framework is really impressive, this is like an extract of the code, but if you have like two machines that are down, there is a probability that we are going to swap the disks of the machines, which means that we are not only trying we are not just testing network partitions, reboot of machine, but also disk and so on. And all of this is going to happen concurrently. And this is the interesting part, is that because everything is deterministic, for a given seed, you will obtain the same results. So this is like an example of how it is run. So you are going to see, let me just, oh, cool, I have a laser. So we are going to fire like the FDB server, which is like the binary of OnNationDB. We are going to say, hey, this is raw. We are going to start in simulation. We have this the test file that we are going to run. We active a Bugify, which is like introduce some errors, and then it is going to generate the seed here. And from this seed, we are going to generate the whole scenario. And for example, in this scenario, we are going to enable a feature called TSS. And in mode 2, okay, and we are going to start a topology with 2 data centers. And we have like this huge number of parameters, which are the layout of the cluster. If we are starting another run of the simulation, we will have another seed, which means a totally different scenario with different failures, different data centers, different configuration of the machine, and so on. And this is what is really interesting, is because for each seed, you will have one run of simulation which do stuff and will have failures and so on. You just run another run, you will have a total different execution style, but all of them are deterministic. And this is really nice because it means that we have improved a lot the developer experience. So what we are doing now in Clever Cloud is that we are running the simulation in a loop, which means that we have workers that are trying to find a faulty seed. So we are just running simulation endlessly. And if we have something that is faulty, we can just report it. So we developed like a Slack bot, which is like showing which seed, which workload, and the commit. And with this information, any developer can just take the information and locally debug the error. And this is like game breaker for developing and writing software, especially in R&D. And because it's like a simple application which is running some bash command on FDB server, it can be deployed as a container, as a VM, as a cloud native app. We don't care. We just like spreading the load and like searching for this faulty seeds. And I'm happy to announce that we are open sourcing this work. So the PR is still not merged because I didn't have time to merge it and fix some CI stuff. But we are open sourcing this work in Apache 2. And this means that if you want to use Foundation DB, you will be able to run simulation and embed your Rust code into the Foundation DB simulation, which is something I think we are one of the first binding which is capable of doing that in truly a deterministic way. So the Foundation DB community is kind of really interested into our work, and we are really happy to be able to open source it. So this was my presentation about simulation-driven testing. So quick pros and cons. The main idea for simulation-driven testing is that it reduces operational burden, and it allows us to replicate real-world conditions, because we all know that network partitions will happen, disk will fail, production will just inject some randomness, and we are sure that if we are passing a certain number of seeds, we can trust our software. And if we are finding something that is faulty, we can reproduce in dev mode locally on your machine. So this is really nice. And yeah, the main idea is that we have a lot of trust into our software, even though it's still labeled as R&D on our side. We are pretty confident that when we are doing a release and deploying it, we are sure that we are not 100% sure, but we are really confident about the fact that major item like network partitions are handled. And so this is the good part. The less good part, let's say, is that simulating everything is really hard. We were lucky to be able to reuse Foundation DB simulation framework because it was it would have been impossible to just rewrite a simulation framework from scratch, I think, on our side. It could be resource intensive, because if you want to crawl the number of possibility really fast, you need to be able to throw some hardware to it. So we are a cloud provider, so it's really easy for us to spin up some machines for us, but it's you need to throw some hardware in it. And one of the downsides is that sometimes validation of the simulation results can be difficult. And on our side, what we are doing, and for now, this has been the main way of writing simulation workflows, is that we need to keep a model of that what should happen in memory to be able to compare. And sometimes it's kind of tricky to write this in-memory model and keeping it in sync about what's happening. So sometimes, be able to check and validate our simulation can be quite tricky. And I think this is it. So thank you for listening to me. Thank you, Sébastien, for having me record this talk.
That was super, super clear, super interesting.
Thank you.
Yeah. And I love the simulation-driven development. You know, I'm a developer advocate. I'm more an airport-driven development. Or conference-driven development.
Yeah.
And about the PR that was not merged, maybe by the time that this video will be processed and put in the queue of maybe it will be merged. So
I hope so.
I guess that if you are open sourcing it, you are hoping for some kind of contributions as well. Are there some areas, fields, or bugs or documentation? Is there something that you're really hoping that people will contribute to? Or
yeah, so we are co-maintainer of the Foundation DB Rust binding. I really think that the community is really growing, because we are seeing like more and more people using Rust in Foundation DB, but because it's a great fit. And so the contribution, there are more end users, but not, we are starting to see contributions, which is really good. But because the way the binding has been designed, there is a lot of simulation and test and so on. So in the functional, it's working great. So we don't have many need of a contribution on the core, but on the documentation and awareness on how to design stuff, we are really looking for contributions. Yeah.
Okay, cool. Yeah, I'm sure some engineers here at Ivan will be really interested in this. So when the video will be released, I will make sure that they watch it. The slides, I can see you have a link there. And if there's any other documentation, you will send that to me, and I will put that. That will be in the description of the YouTube video. And yeah, other than that, thank you again so much. Maybe in a few months we can do a second edition, or maybe even a live stream with, and I can invite some people from my team. I know someone from my team that will be really interested in that, and he would have some really specific questions that I'm not even able to imagine. But
yeah, so I'm looking forward for these questions.
Yeah, exactly. So anyway, thank you so much. See you soon. I see you. Well, it's a recording.
Next week.
We see each other next week. We see each other. We saw each other last week and next week for the other. And okay. Hey, thank you so much, and
thank you.
All a nice day.
Have a nice day.